The broadcast is now starting. All attendees are in listen-only mode.
Hi, thanks everyone for joining us today. In today's webinar, we'll go over a recently announced vulnerability in the WPA2 protocol. The researchers who have discovered this are calling it WPA2 KRACK for key reinstallation attacks. So let's begin with what is WPA2 KRACK. So this is a vulnerability in the WPA2 protocol itself. It affects both the clients and the access points. So if you need to patch the network to make sure you're safe from this issue, both access points as well as the client devices will need to be patched. It also does not matter whether you're using WPA2 Enterprise, which is Radius and EAP authentication, or if you're using the version of WPA2 with pre-shared keys. Both of these are impacted. And over the next few slides, we'll see how and which message flow causes this vulnerability. Uh, one big thing about WPA2 KRACK is this is very widespread. Uh, we typically see security issues around a protocol because of implementation issues from some users or some client devices. In the case of WPA2 KRACK, the vulnerability is in the protocol itself. So it impacts all devices, even if they have strictly followed the security protocol. In the WPA2 KRACK case, when you have an attacker who's attacking the network, the attacker will be able to decrypt some packets, will be able to replay some multicast and broadcast packets. He'll be able to inject packets a second time into the network. Um, we also have some client-side issues, primarily on Android, where some of the clients can be forced to zero out their encryption key. So instead of using a nice random encryption key to encrypt their packets, as a result of this attack, the clients get into a state where their encryption key becomes all zeros, and at that point, the attacker can decrypt any packet from this client. Now, having said that, the attacker will not be able to recover the WPA2 passphrase. So if you are using pre-shared keys and you have a strong random pre-shared key, that can't be recovered. Um, you can't inject arbitrary packets as long as you're using AES CCMP, which is the recommended standard for WPA2. And you also cannot decrypt packets without being present near the network. So this attack requires the attacker to be right in the middle of the connection between a client and an access point. And again, over the upcoming slides, we'll go over how this attack takes place. But the attacker has to be on site, has to intercept the packets that he's receiving from the access point and which are being sent to the client. And then while doing this interception and forwarding, there are certain things you can do which exposes this vulnerability. So how does this work? WPA2 KRACK intercepts and replays some parts of the handshake. So when a client connects to an access point, it goes through what's called a four-way handshake. So after a client associates with the network, it exchanges 4 messages with the access point. These messages are used in WPA2 for confirming that both the client and the AP have the right encryption key, to derive a session key from that, which will then be used for all the encryption, and for the client to receive the broadcast key with which it would decrypt all the packets that it receives from the AP. So this handshake that happens on each and every client association, this handshake is exploited by WPA2 KRACK. And the way they do that is by forcing the victim, which could be the access point or the client, into reusing a packet number for the same key. So just bear with me for one more slide. We'll go over why this is an issue. And the attacker would typically be a man in the middle here. So this would be somebody with a laptop and 2 wireless cards. One of them typically on a different channel associated to the access point. The second one acting like an access point towards the clients. So now when a client sends a packet to the access point that he thinks he's sending it to a proper, well-known access point, being intercepted by this attacker, and then is forwarded out the other radio card onto the real AP. And then similarly, in the other direction, any downstream frame from that AP is intercepted by the attacker's laptop on the first radio card, and then forwarded out of the second radio card back to the client. So the client doesn't know that there's someone in the middle. Frames are being exchanged, it goes through the handshake, but there are certain things the attacker then does which can force the client to become vulnerable. There are various handshakes. The four-way handshake that we just talked about is the most common handshake that happens in WPA2 Enterprise. There is also a group key handshake, which in the four-way handshake, the group or the multicast key is passed on to the client as part of the handshake itself. In the group key handshake, this is a separate handshake that happens if you want to just update the multicast keys on all your clients. And then the last kind is, so in 802.11r or fast BSS transition, the IEEE standards made some updates to to the roaming, saying instead of having these 4 messages on each roam, which can delay roams, um, we combine these into the association and authentication. So there are less frames exchanged on the air. So that makes the roam faster, but that handshake is also vulnerable. So there are 3 different kinds of handshakes when a client connects to the AP, and all of these 3 are vulnerable to this WPA2 crack attack. So crack attack, the basic exploit is to make sure that a device reuses a packet number. So why is this bad? So let's consider an example where we have 2 messages, message 1 and message 2. So these are plain text packets, and these are then encrypted. So you have E1, which corresponds to message 1 encrypted, and E2, which is message 2 encrypted. Now, if we were to write this out as a function, the encrypted packet is the message 1 XORed with this AES stream containing the key and the and N, which is the number 1, so the packet number. So as long as the key is the same and the N keeps changing, you will keep getting a different value of the encrypted packet for M. Similarly, if E2, when you pick up message 2 and you encrypt message 2 to get the second encrypted packet, as long as this N has changed, then you get a different encrypted packet, which is fairly safe. Now let's assume an example where you have somehow forced the client to carry out encryption of M1 and M2 with no changes to the key and no changes to the nonce. So now when you do this, the encrypted packets that you get, because of the way the encryption works in the stream ciphers, the XOR of the 2 encryptions is the same as the XOR of the 2 plain text packets. So what this basically boils down to is, if you can guess the contents of one of those plain text packets, then you can guess the contents of any other packet. So that's the vulnerability that WPA2 crack opens up. Forces the client to reuse the packet number, and then when the client reuses the same packet number, the packet that it sends out, if you can guess the contents of one of those 2 packets which have reused the packet numbers, you can guess the contents of the other packets. Now, in networking, there are several protocols where the packet contents are either fully or partially known. And this is something that the attacker can use to then guess the contents of your actual data packet. So for example, a TCP SYN packet, if you know the IP address of the client, then you can figure out most of the TCP SYN packet. Similarly, the contents of an ARP or the contents of a DHCP discover packet. So there are a number of these packets where the overall content, or at least parts of the packet, can be guessed by the attacker. If you can force a client or an access point to encrypt 2 packets, one of them which is of a known content and one of them which is your actual data packet, you can now guess the contents of the data packets also. So there are 3 separate attacks that the researchers have come up with, and these are the attacks against the 3 separate handshakes. So there is an attack against the 4-way handshake, which tricks the client into resetting its packet number. Once this attack is carried out, the attacker can potentially replay a packet from the access point to the client. The attacker can also decrypt client to AP packets. And so one thing to keep in mind is, in all of these cases, it's not a vulnerability like the way web was broken, where you could just take a packet capture and analyze it offline and pretty much decrypt the whole web stream. At this moment, this is more a research level vulnerability than active exploits going on. And also, when we say decrypt the client to AP packets, uh, the attacker is not able to derive the key. The attacker can only decrypt some contents of some packets. So that's the level of the breach in the protocol. Similarly, the FT association, which is the 802.11r handshake, in this case, the attacker can trick the access point into resetting its packet number. And we'll go over some of these packet flows to see how this is achieved in real life. And then lastly, against the group key handshake, where again, it's the client that is tricked into resetting its packet number. There's no decrypt in this case, but this allows the attacker to inject a second packet towards the client. Now, In all these cases, the encryption is assumed to be AES. WPA and WPA2 also had TKIP as an intermediate encryption protocol before AES became widespread. All of these attacks are worse with TKIP, where there is potential for injection of arbitrary packets. So the attacker can create a packet, craft any kind of packet he wants, and inject that into the network. That happens only if the encryption is TKIP. As long as you're using AES encryption, you're not impacted by that attack. So we've been talking about these four-way handshake messages and how these are exploited. This call flow kind of shows what the four-way messages are. So each time a client associates with an access point, it goes through the first four messages, which are authentication request response and an association request response. These messages are done irrespective of the encryption type. So even if you're doing an open SSID, each time a client roams to an AP, it would go through these four messages. After that, depending on the encryption type, if you're using WPA2 enterprise, you might do radius authentication. If you're doing WPA2 pre-shared keys, then you move straight away to the four-way handshake. If it's enterprise, we would do the radius auth, and then we would move to the same four-way handshake. And then this four-way handshake are the four messages. So message one goes from the AP to the client. The client then sends a response back. In these first two messages, the AP and the client exchange random numbers. So these are used in the derivation of the final session encryption key. And then in the third message, the access point sends to the client the GTK, which is the group encryption key. This is the encryption key that is used for all the multicast and broadcast packets on the network. And then in message 4, the client acknowledges that it has received this. And at this point, all the data packets can be transmitted by the AP and the client. The group key can also be handled separately. So there are some implementations where you would want to update the group key either periodically or let's say each time a client leaves the access point. You don't want to use the same group key that is now with some client which is no longer part of your network. So just as a security practice or periodically the group key can be exchanged. So that's the last two handshakes, the group key update from the AP and an acknowledgement back from the client. So let's go over the first attack. This is the attack where the four-way handshake itself is attacked. So you have three devices here. On the left, we have the client, which is the supplicant or the victim. Then the adversary is this man in the middle. So a laptop with say two radio cards. One of them which is tuned to the channel of the access point or the authenticator on the right. And the other one is a card which is acting as an access point towards this client. So now the client associates, the client thinks he's associating with the access point on the right, but he's actually associated with this man in the middle AP. And once the four-way handshake begins, the AP sends message 1. This is transmitted as it is to the client. The client then sends back message 2. This is also forwarded as it is to the AP. And now when the access point sends message 3, instead of forwarding the client's response all the way to the AP, the adversary blocks this packet and prevents it from being forwarded. Now the client doesn't know that message 4 did not make it to the AP. So the client starts encrypting packets. So that's the first encrypted packet we see there, ENC1, right below the install PTK and GTK. Now having not seen message 4 come by, the access point would retry message 3. So that's what we see in block number 3 there, where message 3 comes back from the client, from the access point. And this time the adversary forwards this packet over to the client. So now message 3 goes to the client, message 4 comes back, and on the receipt of message 3 again, the client goes through the same process that he just did. So he reinitializes the key, reinitializes the packet number, and starts using these new values for the packets that he's sending out. Now he sends a message 4, and this can then be forwarded by the adversary to the authenticator. So both ends are now happy, thinking that all of the encryption has been set up, the handshake is complete. But what has happened in the interim is the client at stage 2 had sent out some data packets, potentially a DHCP discover or an R packet, or even some existing TCP connections packets. And the same packet got replayed later after the reinstall of the key. So now we have ended up forcing the client to send the same packet 2 times with the same encryption key and with the same packet number. So this is a vulnerability in stream ciphers. And once an attacker can intercept and capture these 2 packets, if he can guess the contents of one of them, he can start guessing the contents of the other packet too. So this is the first attack. This attacks the four-way handshake. The second attack is against the group key handshakes. So this is where an access point would periodically update the multicast or broadcast group keys of the associated clients. And here again, we have the adversary in the middle who's got these two radio cards, one of them listening to the access point, the other one towards the client, receiving and forwarding all the packets, but then deciding not to forward some of them. So in this case, the AP starts the handshake by adding its new encryption key, the new broadcast and multicast key, and by transmitting the group message one across to the clients. So the client installs this new group key and sends an acknowledgement back. The attacker blocks the message two back from going back to the AP. So after a while, the AP, in the meantime, the AP has been transmitting encrypted packets. So the AP doesn't know that the packet is being blocked. The AP realizes that this group key one has not been acknowledged by the client. So he sends another update. And this time the attacker forwards it to the client. So the client again receives this group key and the client starts to reinstall the same key, but resets the packet counters back to the old value. So now you again have a case where the client has reset its packet counters, and this the encrypted packet that was sent in the middle, this can now be replayed by the attacker. So in the group key handshake case, there is no decryption vulnerability, but what the attacker can do is re-inject packets into the network. So it's an encrypted packet sent from the AP, which has been intercepted and is being retransmitted. In most normal cases, the client would drop this packet because the packet number would have increased. So if you've got packet numbers 1, 2, 3, and then let's say he receives packet number 2 again, the client would drop that packet saying, I've already seen 2. But in this case, because the resetting of the packet numbers, we're able to re-inject that packet back into the client. And lastly, the 802.11r fast transition handshake. So in the case of 11R, when we saw the four-way handshake, we saw there were 4 packets first, 2 for authentication, 2 for association, and then the four-way handshake. That's a lot of packets to exchange each time a client roams from one AP to another. So what 11R tries to do is speed up that process by reducing the number of messages. And the way they've done that is by incorporating some of the contents of message 4 into these first 4 messages. So the auth request, for instance, contains some of the random numbers from the client. The auth response is doing some of the work of the message 2 of the handshake and so on. What this also does is open up the same vulnerability where this time the adversary is able to replay a reassociation response. Um, and with the replay of this packet, the access point ends up resetting his packet counters. And in this case, this is something that can happen at any time on the air. Packets can be lost. And this is in addition to reassociation response, even the previous messages that we saw, access points allow for retries because packets can be lost because of noisy or bad RF conditions. So if a packet comes back again, an access point or a client is typically engineered to accept that packet, reset everything, and start the whole process of encryption again. The patches that are going in now is to make sure that we don't reuse the same key and the same packet number. As you had mentioned, there are patches for both APs and wireless clients, so both sides need to be patched. There are some temporary workarounds on access points. So the four-way handshake attack is primarily aimed at the client. The one case where an access point acts as a client is when it is a repeater or a mesh client. So that's one case where an AP becomes vulnerable. And then the 802.11r attack is something that is also aimed at the access point. So the two temporary workarounds are to disable the client or repeater mode if you can use a wired connection and not have a repeater, and disable 802.11r. So the disabling of the client mode does impact functionality. 11R would basically slow down some of the roams and connections from the clients as they move between the APs. The other always good practice is to ensure that there is good upper layer security for sensitive data. So Wi-Fi encryption is only between the client and the access point. So for instance, if you are accessing a website which is asking for your login information, it's always good to make sure that the connection is HTTPS, which is usually indicated by a padlock or a certificate information in the URL of your browser. Also, you should use VPN whenever possible. This would again give you end-to-end encryption. So if you're accessing any sensitive information on your corporate network and you have a VPN server, then that would also work around this issue. Now there is a potential AP workaround where just patching the AP might be enough. If the AP were to not retry any messages, but this comes at a risk because without any retries, if it's a noisy environment, then you would have increased handshake failures, you would have roaming issues, and clients would potentially also have connectivity problems. So there are cases where clients are either slow in processing the first message, or as the handshake walks down the ladder diagram, there are some messages which take a long processing time from the client, and they may not respond in time. So without retries, that would result in a failed connection, and the connection would have to start all over again. And we have seen some cases where a client can get stuck in this loop of not being able to associate with the AP. So a couple of things to keep in mind for administrators. There are a number of things which will not help with this vulnerability. For example, changing the passphrase to a longer or a stronger password will not have an impact. The attack is on the handshake itself, and the vulnerability again is the reuse of the key. So it does not matter if your passphrase is strong or if you're using 1 2 3 4 5 6 7 8 as your password. Uh, you'll be vulnerable either way. And then switching between WPA2 Enterprise and WPA2 PSK also does not help. So if you have a pre-shared key network, you may want to move to Enterprise for other reasons, since you can have control over access on a per client basis. But as far as this vulnerability is concerned, both WPA2 PSK and WPA2 Enterprise are impacted. And the last one, somebody brought us up, was switching to web. So web is a much more broken protocol than anything that we have discussed here. So do not switch to web. Apply the patches, and as a temporary workaround, if you're not using mesh, and if you're not using 11R on the access point side, you're okay. Make sure all the clients are patched. Also note that this attack right now is relatively difficult to carry out. It does require man in the middle presence. It also requires some non-ski guesswork to actually decrypt the packets. And there are countermeasures that are already being rolled out. So software patches from different vendors for both access point as well as client devices are being rolled out. So coming to our Cambium products, the Wi-Fi APs are affected by this. So the CN Pilot Enterprise APs are affected in both mesh client mode as well as in when 11R is enabled. 11R is off by default. There's another fast roaming technique called OKC, opportunistic key caching. So that is not affected by this particular issue. So you can leave OKC enabled, but until you have the patch in place, disabling 11R would be recommended. The CN Pilot home APs, the R series, are also affected by this in repeater mode. The EPMP product line is also affected since it also uses a similar handshake. And other Cambium products are not impacted by this vulnerability.
Yeah, Puneet, I'm just jumping in on the EPMP product line. Just a minor comment that with EPMP, it is even way more complicated to use this vulnerability in a real life, because we are talking about the proximity to both AP and SM, and you have to repeat all the TDD protocol we had to use this vulnerability. And as far as we know, nobody yet repeated our TDD protocol in the wild. So it is very, very complicated attack, but we obviously fixing it.
Yeah, that's a good point, Dimitri. So on the Wi-Fi APs, we do the standard Wi-Fi protocols. So these would be more easily vulnerable to test tools and vulnerability assessment tools. So coming to software updates, on the enterprise access points, we have patches that are right now currently in test. Software version 3.4.3.5 will be releasing this week with patches for this vulnerability. On the home access points, we are also in testing of some of these changes. The planned release is the week of November 13th. So we'll have updates to R190, R200, and R201. And if you're not using repeater mode, then again on the home series, you're okay, you're not affected on the access point side by this vulnerability. The home routers do not support 802.11r, so they're not affected by that last attack. The software, as soon as we have the versions out, they will be made available in both CN Maestro as well as on support.cambiumnetworks.com. So for more information, there are three websites. Crackattacks.com is a website set up by the researchers themselves who have discovered this vulnerability. This has a lot of information on what they have found, how they found it, and a paper that goes into a lot of details of the attack. And community.cambium networks is our forum where we are posting updates. We have an advisory out on the forum as well for what to do with this attack. And then cert.org. So cert is a knowledge base of vulnerabilities across the networking and pretty much across the industry, the technology space. So cert also has some vulnerability details listed out on their website for WPA2 crack. As well as the vendor status. So cert is also keeping track of as and when vendors are releasing patches, the date when the patches are being available, and links to the vendor web pages for WPA2 crack. That's also all being maintained on cert. Okay, that's pretty much it from us. Let's see if there are any questions.
Yeah, I have a few questions from the side channel. So one of the questions that, okay, so if we're going to update clients, is there any way to detect or possibly drop outdated subscribers?
So that's a good point. So in our logs, we would see replayed messages from these clients, but the catch is in a very noisy environment, there is also the possibility to have a replay. So all of these attacks are exploiting replaying of messages, but it is always possible to the messages could be lost due to noise or interference as well. So a replay could be an indication of an attack, but it's not a for sure sign that the network is currently under attack. The other thing is on Android, this is actually it's a widespread vulnerability. There are some estimates that 60 to 70% of all Android devices are affected. So this might, on the client side, this might take some time to work through all the
And
devices.
as far as I know, on the Android part, it is even worse because they're using the zero key.
That's right.
Android
So in
versions.
addition to so in addition to just reusing the packet key, Android, lots of versions of Androids also zero out the encryption key on their side, which makes it even more vulnerable than usual.
Okay, one more question we have, when it's going to be available for EPMP, the update. So right now we have patches in the QA, so we're testing it in the QA, and we're going to release it to public on the next week. We're targeting November 10 right now. One other minor comment, which I find pretty funny, that we use open networks in Starbucks, but right now we care about the KRACK vulnerability that can possibly decode.
That's a good observation. Yes. So yeah, that's an interesting observation. And just to reiterate there, right, at the end of the day, it's more important to make sure that your end-to-end network is secure. So for instance, if you're accessing your bank's website or even your email, make sure it's an HTTPS connection.
Okay, one more question. So if it is affecting client side, does it affect only this client or it affects everyone on that network?
So the replay attacks and the decryption would only affect that client. So the session key that is derived is per client, and what you would be decrypting would be packets from that particular client. So if you have another client that has already been patched or is not vulnerable, then just having one of these unpatched clients come on the network does not compromise your whole network. It would compromise that client. Now this is with AES. With the TKIP, since you can arbitrarily inject packets, it opens up lots of attack vectors into your network. So as long as you're using AES, any vulnerability from an unpatched client would be restricted to impacts to that client.
And Puneet, is it even possible to set up TKIP on CNPilot right now?
So we have a CLI only option for, only meant for cases where someone has devices which are not yet capable of AES and are being phased out. But in the normal case, no, we support only AES with WPA2 or open for the public Wi-Fi cases.
Okay. So the next question, the other vendors, users of other vendors have noted a latency increase after upgrading to the patched firmware. Is there a potential with the ePMP firmware? As far as I know, and I had a call with our developers today in the morning regarding this issue, and on our first QA cycle, we didn't notice any latency increase or throughput degradation because of those fixes. So we don't expect latency increase. Okay, the next question is what is the name of vulnerability? So the name is KRACK, right?
Yes, the name is KRACK, and this is a sort of acronym they have made up called key reinstallation attacks. So KR for key reinstallation, and then the ACK from the attacks. So that's the name the researchers have given to this.
What are the precautions for it? So the precautions for the vulnerability, I believe.
Right. So on the enterprise access point, if you're using mesh client mode, so that's when you would potentially be open to this. And the other attack vector is if you have 802.11r enabled. That's the other case where an access point can be vulnerable to this. So until the patch release is out and you've updated the access point firmware, if you can avoid mesh, and again, this is not a case where the protocol is broken and everyone's able to easily encrypt all easily decrypt packets. This is a flaw that has been discovered, and there are potential issues with decrypting. If you have a very mission critical network, then leave mesh on for a few days until the patch firmware is out. 11R can be easily disabled without much impact to service.
Okay, so probably that's it. Thank you, Puneet. It was a great presentation, and I believe everyone else enjoyed it. So thank you.
Thanks, Dimitri. Thanks everyone for joining us today.